Visualizing data, part 2. You ever have one of those moments where you realize you fundamentally think about the world differently than other people do? So when that happens, you start to see certain solutions as super obvious, and it's not until you talk to somebody else that you realize that maybe it's not so super obvious, because those people find your solutions strange.
That guy's a weirdo.
That happened to me when I published the paper that I'm linking in the description. In that paper, we were really advocating for a new way to visually identify interaction effects. And the reviewers were saying stuff like, we know how to find interaction effects. There are lots of ways to find an interaction effect. Just use stepwise regression or a hypothesis test. And in that moment, I had a realization that I was thinking about the world very differently than these people were. Because most people do data analysis very differently than I do. Most people start with their hypothesis tests, and they might even include an interaction in their hypothesis test, like in here.
Yay, it's statistically significant!
And if they do find an interaction, they might visualize the interaction, usually without raw data, which is stupid. In other words, they begin with a hypothesis test, and then they follow it up with visualizations, maybe. I do it very differently. And if you want to know what my strategy is, I'm going to link my 8 steps of data analysis paper, because this really outlines my strategy for visualization. For me, visualization is not an afterthought. Not at all. It is the foundation. I start from the very beginning with visualization. Then I use those visuals to build my statistical model. So if the visuals suggest an interaction, I model an interaction. Now, why am I saying this? So in my last video, I realized I didn't make that explicit. What I should have said is,
I am showing you how to build models by first visualizing the data.
And in that video, I mentioned that it was important to identify nonlinear relationships and interaction effects, but I didn't tell you why. I should have said, quote,
We are looking for interactions and nonlinear effects because those inform us about the type of models we need to build.
Because here's the thing, let me level with you. The biggest danger to modeling is to miss something that could have been modeled that you didn't model. And 2 of the most common things that are missed are interaction effects and nonlinear effects. And if you miss those effects, your model is basically meaningless. So we want to, at all costs, avoid missing something. So how do we make sure that we've modeled everything we can possibly model? Why, by golly, that's the purpose of this video.
Oh, now, wait a minute. Didn't you say in the last video that your next video is going to be about identifying 3-way interactions?
Did I say that? Huh. Oh yeah. Same thing.
What?
Well, think about it. If there's a 3-way interaction and you haven't modeled it, then you haven't modeled everything you can.
Ah, good point.
So let's look at an example model. Let's say you have the following true model. In other words, this is what the model actually is in reality. Of course, you never know this, but let's just say that we know it. This model says that suicide ideation is made up of a main effect of health, a nonlinear effect of stress, and an interaction between friend ideation and depression. So that's the real model, but the model that we've actually fit looks like this. So we have the main effect of health, we're good there, except we're missing the nonlinear effect of stress, and we're missing the interaction effect between friend ideation and depression. So how would we ever know that?
How could we possibly know what we were missing?
We need a tool. And that tool is partial residual plots, but I'm not gonna tell you about it right now.
Well, that's just rude.
Hey, my channel. I do what I want. Before I tell you about partial residual plots, I'm gonna review added variable plots. So let's say we have this data set. We've got x1, x2, and y. And let's say we want to know what the effect is of x2 after controlling for x1. With added variable plots, we first fit a model with x1 as a predictor. And let's say our model looks like this. Y is equal to 1.1 plus 0.7 times x1. Now let's go ahead and look at our data set and now add the predictions to that data set. So if we go 1.1 plus 0.7 times x1, which is 0.7, then we get a prediction of 1.8. And likewise, for the second row, if we add 1.1 to 0.7 times 2, we get 2.5. And so on, and so on, and so on, and so on, so on. And the second step of making an added variable plot is to compute the residuals. And the residual is just the difference between the predicted value and the observed value. So our residual here is 2 minus 1.8, which is 0.2. And the residual here is 2 minus 2.5, which is negative 0.5. Etc., etc., etc. So now, once we have this data set, we can plot our new variable, x2, against these residuals. Like that. So this plot shows the effect of x2 on y after subtracting out the effects of x1. And this is an approximation of what regression is doing. Because if we were to fit the entire model with x1 and x2 in it, each of these slopes represents the net effect after subtracting out the effect of the other variables. But with added variable plots, this is just an approximation. Because here's the thing, regression models are not sequential. It's not like we fit x1, subtract the residuals, and then predict those residuals from x2. That's not what happens. It's all done simultaneously. And for that reason, an added variable plot is just an approximation to what regression is actually doing, as in this plot. And so you'll see in this plot, the blue line here is what you would get by doing it sequentially. Or in other words, the blue line is the added variable plot, whereas the red line is the regression line, which again estimates things simultaneously.
Well, I'm just not okay with approximation. It needs to be exact.
Don't trouble your feeble mind, my friend. There is another tool called a partial residual plot, or a PRP, or a PERP, or a PRP, partial residual plot. Just like with added variable plots, we can use partial residual plots to look at the effect of one variable after subtracting out the effect of another variable. Except with partial residual plots, the added variable plots are going to be an exact representation of a regression model. Exact. So how do they work? Oh, good question that I asked myself. Really should have put on a different hat when I asked that question. Oh, it's not too late. But I already forgot the question.
How do they work?
Good question. Let's say we have a model with x and z as predictors, and we're trying to predict y. And let's say we want to know the effect of z after removing the effect of x. Sounds like fun. And by the way, this part gets a little technical. I'm tempted to say, if you get confused, don't worry about it. But it's kind of important to understand it, so do worry about it, I guess. But don't stress it too much that you shorten your lifespan, I guess. Just watch the video again, and I'll try to explain it slowly. How's that? So the first thing we're gonna do when we're creating a partial residual plot is we're going to fit the entire statistical model. And I'm gonna put some notation up on the screen. Don't get scared though, it can't hurt you. So our entire statistical model looks like this. Y is equal to b0 plus b1x plus b2z. Hopefully y'all are familiar with that. Not too scary yet. Then what we're gonna do is we're gonna calculate the residuals from this entire model. And we're gonna call these residuals E with the subscript of y given x plus z. Or in other words, these are the residuals from a model predicting y from x and z. Step 3, which is probably the most important part, so we're going to take these residuals that have subtracted out the effects of x and z, except now we are going to add back the fit of z. Because remember, we want to know the net effect of z after subtracting out x. And so we want residuals that contain just x. And so to do so, we're gonna take these residuals, E subscript y given x plus z, and add to them the slope of z times the values of z. And we call these residuals E subscript y given x not z. That's what that funny sideways hockey stick is called, the not symbol, I guess. Hey, I didn't make it up. And what that gives us is residuals from the entire model, except we're adding back the fit of z into it. And so it's only removing the effects of x, but not z. And then we can plot z against these new residuals. And the very cool thing about this is it becomes a very exact, very precise, very perfect, very amazing visual representation of exactly what a regression model is doing. In this plot, it shows the line from the partial residual plot overlaid on the actual regression line.
Wait a minute, I can only see one line. Is anybody else having the same problem? I can only see one line.
Yeah, that's because they're the same line. Because again, it is a precise visual representation of the regression model.
Oh, I get it. Yeah, that's pretty cool.
Cool doesn't begin to describe it. Let me review. We want to build a model from the visuals, not visualize a already built model. But we need a way to visualize that model. And we also need to know from visuals if there's something in our data that we have missed. Added variable plots, which I talked about last time, and I talked about a little bit this time too, show us exactly what the model fit. But one of the problems with added variable plots, which is what I mentioned last time, is they cannot be used to visualize interaction effects. using added variable plots is only justified if the variable on the x-axis has no interactions whatsoever. And another limitation with added variable plots and partial residual plots is they don't naturally tell us what the model failed to fit. Or do they? All right, this is where it's gonna get cool. So let me just say that I invented partial residual plots 70 years after somebody else invented them. I really hate it when I get scooped like that. In other words, I didn't invent partial residual plots. I just realized somebody else had already done it. But I did extend them. Because here's the thing, traditionally partial residual plots are bivariate plots. But I started thinking, hey, partial residual plots, they don't need to be bivariate. Why not make them multivariate? So let's think of an example. Let's say you have the following model. Suicide ideation equals B0 plus B1 times stress plus B2 times depression plus B3 times friend ideation plus B4 times friend ideation by depression. It would be super nice if we could visualize the interaction in this model. Now, of course, we could just visualize that model by ignoring the fact that stress is there. But let's say we still wanted to visualize the multivariate model where stress is actually a predictor in that model. What do? Maybe what we could do is we could use partial residual plots, but we could visualize a model where the y-axis has the residuals from just the stress variable. Like in this example. In this model, our residuals have just subtracted out the stress variable, but not depression and friend ideation, which allows us to now look at a multivariate plot, assessing the relationship between depression and friend ideation after controlling for stress. That's pretty freaking cool. And so what we find in this model is the more friends you have who are suicidal, the stronger the relationship between your depression and your suicide ideations. But if none of your friends are suicidal, then there's no relationship whatsoever. By the way, this is a made-up data set that I made up. Yeah. So that is the Dustin extension to the partial residual plots. I should probably come up with a better name though. The Fife modification theorem. The Fife PRP modification theorem axiom standard. That's good. I like that. Now you're probably wondering, hey man, how do I do a partial residual plot in flexplot? Because that'd be cool. It requires 4 arguments. One is plot formula, and this controls how the plot is displayed. And by the way, the syntax is identical to what it is with flexplot. Model. That is the entire model that you fit. Added underscore term. And what you put in there is the terms that you want to add back into the residuals. So in this picture, we added back into the residuals the fit from depression and the fit from friend ideation and their interaction. Again, so we could visualize what the model is saying about these variables and these terms. And then finally, the data set. So to reproduce this plot, the partial residual plot code would look like this, where this here is your model, this here controls the visuals of the plot, this right here controls which variables are subtracted out from the residuals, and this is where you specify the data set. So partial residual plots are actually a pretty phenomenal tool. We can use them to visualize main effects, just like we did with added variable plots, but we could also use them to visualize interaction effects. But you remember earlier how I said it'd be so cool if we had a tool that could tell us what the model didn't fit? Or in other words, wouldn't it be cool if we could visualize the unmodeled effects? Well, you can with partial residual plots. When you are trying to visualize unmodeled effects, here's the basic idea. This isn't my idea, by the way. This is basically what a residual analysis is. So the basic idea is that we assume that our model captured all the signal or all the patterns in the data set. And once we subtract out all the signal or all the patterns in the data set, which is what the residuals are, at this point, these residuals should be completely random because we subtracted out the fit from the entire model. Or in other words, there should be no relationship between our variables and the residuals. So then we plot these residuals against all the variables in our model. But if we see a pattern, that means we've missed something. So let's look at an example of that. Remember earlier I said in our true model, stress has a quadratic term to it. But let's say we fit this model. Ideation is a function of stress, but only a main effect, and depression. Now let's go ahead and visualize the unmodeled effects. And to do that, here's what our R code looks like. So again, we specify our model first, and then for the plot itself, we want ideation on the y-axis and stress on the x-axis. And we're telling it our residuals come from this model, and then we say added underscore term equals null. Or in other words, we're not going to add back to the residuals the fit of any of the variables. Because again, we want to see what wasn't modeled. Because remember, when we add a term back into it, that puts signal back into the residuals. We don't want that signal anymore. We want just the residuals. Because again, we're looking for unmodeled effects. And then we specify our data set, data equals ideation. And if we visualize this, we would find a plot that looks like this. Remember, our model should have a quadratic term, but we didn't fit that quadratic term. So this partial residual plot is telling us that there's still some signal in the data that we haven't picked up. So what's happening here? In this plot, our residuals reflect the fact that we subtracted out the linear effect of stress and the linear effect of depression. Now, when we plot stress against these residuals, we still see a pattern. That means that our stress variable is still correlated with our residuals, even after removing the main effect of stress. In other words, there is a pattern in the data that we failed to fit. Technical aside, I've been calling this a partial residual plot, and some of you might be saying, hey, isn't that a residual dependence plot? And yeah, it is. Residual dependence plots are a special case of partial residual plots, at least in the way that I conceptualize them. Let's go ahead and look at another example. Remember how depression and friend ideation interacted with one another? Let's just pretend we fit a model and didn't realize that. So we've got a model where ideation is equal to a main effect of friend ideation and a main effect of depression. Again, we didn't model the interaction. Now, if we look at a partial residual plot, and you and I know that those two are interacting with one another, and if we plot depression on the x-axis and friend ideation in panels, we specify our residuals come from this model, and we say added term is equal to null, because again, we don't want to add anything back to the residuals. We're just trying to look if there's anything that we missed. And then we go data equals ideation, and I'm going to go ahead and add method equals LM. And basically what that's going to do is it's going to look at the raw data and fit a regression line to it. And this regression line doesn't come from the model, it comes from the actual plot. And so what are we finding? If we look at the far left plot, our model says that there's no relationship between depression and friend ideation in any of these panels. That's why all those red lines are flat. That's what our model suggests. But if you were to overlay a regression line on each of these panels, you would see, holy matoli badoli. There's a relationship there. You done missed something. This plot is telling us that the relationship between depression and ideation, if your friends have very low suicide ideation, is actually more negative than the model predicts. Whereas if your friend is of average ideation, model does pretty well. But if your best friend is high in suicide ideation, the model, which is the red line, underpredicts the actual relationship between depression and ideation. So do you see how pretty freaking amazing these partial residual plots are? They can tell you what you've modeled, and they can tell you what you failed to model. So let me just summarize again, I guess. The purpose of all this is to use visuals to guide our decisions in building models. We can visualize easily the main effects of a multivariate model using either added variable plots or partial residual plots. Of course, added variable plots won't be a precise representation of the regression model, but it'll be close enough, I guess. But I prefer to use PRPs because they are a precise visual representation. And if we are trying to visualize the main effect of a variable or variables, we just add back those terms into the added underscore term argument. We can also visualize interactions with partial residual plots, at least with the multivariate extension of the partial residual plots. And to do so, we just have to add to the added underscore term argument both the main effects and the interaction effect. And again, we can also use partial residual plots to visualize unmodeled effects. And we do this by plotting the residuals against all the other variables in our model and just trying to see if there's any sort of patterns remaining. And when we do this, we leave the added underscore term argument blank. And now, finally, we're going to talk about three-way interactions.
It's about time, am I right?
Excuse me, there's no talking in class.
Wouldn't talk so much if you were a better teacher.
What was that?
I said you're a great teacher.
Thanks. Three-way interactions. Let's say we have an interaction between x1, x2, and x3. How could we detect it? By partial residual plots, of course. We would start by fitting a model where we have all the main effects of x1, x2, and x3, and any other two-way interactions that we are able to detect, maybe with marginal plots. Then what we can do is we can plot a PRP looking for unmodeled effects. Or in other words, our added underscore term argument is going to be blank, or null, I guess. And then if we were to visualize all three predictor variables using a multivariate plot, like this, we would see, by golly, there's some signal we failed to pick up. Notice those lines are not parallel. Or in other words, there is a pattern between what variables are in our model and the residuals from the entire model. We failed to pick up on something. Our instinct when we have a big old plot like this is probably to look at marginal plots and see if we can identify any sort of two-way interactions that we missed. So if we try to see if x1 interacts with x3, well, no, all those slopes are pretty parallel. Does x1 interact with x2? Well, no, all those slopes are pretty parallel. These off-axis panels don't really help us that much. And we wouldn't expect them to if there's a three-way interaction, because these panels only tell us what the nature of a two-way interaction is. But we can look at the plot and see that the lines are not parallel. So think about that. The marginal plots tell us there are no unmodeled two-way interactions. But when we look at the plot, we can see that those slopes are changing. So what does that mean? That means we have a three-way interaction. You see the basic idea? So again, we model all the two-way interactions we could find, and then we use a partial residual plot. And if we still see non-parallel slopes, and we can't seem to find any sort of two-way interaction left to model, that tells you that there's got to be a three-way interaction there. Let's go ahead and spend some time interpreting this three-way interaction that we're seeing. And to do so, we're going to use the same strategy we used in the last video, where we interpreted the two-way interaction first and then asked ourselves how that two-way interaction changes across the levels of the third variable. And another strategy I'm going to use is we're going to reduce the number of bins. So in this plot, we have 3 bins for x2 and 3 bins for x3. But let's just go ahead and cut that down to 2 just to simplify the visualization. And we get something that's a little bit easier to interpret. So what I'm going to do is I'm going to isolate this panel and try to understand what's going on. So what we are seeing is that for low values of x2, there is a positive relationship between x1 and y. Whereas for high levels of x2, it's actually a negative relationship. So the nature of the x1-y relationship changes from negative to positive, depending on whether you have low or high levels of x2. All right, we good? So what I just described was what happens for low levels of x3. Now let's look at high levels of x3. And what do we find? We see that the nature of the relationship is actually opposite. So rather than having a positive relationship between x1 and y at low levels of x2, we instead have a negative relationship. Rather than having a negative relationship between x1 and y for high levels of x2, we instead have a positive relationship. And of course, these variables, x1, x2, and x3, and y, they're just made up variables. So there's not much substantively that you could pull from that, but that's basically how you would approach it. So let me just do a summary again. And I know this video has been like pretty technical, and it's actually really hard to prepare this video. I mean, the more technical something gets, the more I start to get worried that people don't get what I'm talking about. Anyway, let me just summarize this video. The strategy that I advocate begins with visualization. We build our models from what we see in the graphs, not vice versa, which is what everybody else does. They start by testing hypotheses, and then maybe they will visualize something. We don't want that. And when we are doing this process of building models from visuals, we always want to make sure that we're not missing any sort of effects, that we've modeled all there is to model from our variables. And so in the process of this, we are specifically looking for two-way interactions and nonlinear effects. And by nonlinear effects, usually I'm talking about quadratic effects. And so we do this by looking at paneled plots like this and trying to identify any nonlinear patterns or any sort of non-parallel slopes. If we identify non-parallel slopes, then we can use marginal plots to figure out which two variables are interacting. And if there's a pattern of slopes changing in the marginal plots, like in here, where the relationship goes from negative to positive, then we know that this variable interacts with this variable. And we can identify nonlinear effects by looking at the plot and seeing if the line is nonlinear. And so using these visuals, we begin to build a model. And we can use partial residual plots to visualize what we've already modeled, or we can also use partial residual plots to figure out what we haven't modeled. And so after we fit our entire model and we still see non-parallel slopes in a paneled plot like this, and we have concluded from our marginal plots that there are no remaining two-way interactions, like in this plot, then we can safely conclude that there is a three-way interaction. So at this point, I'm thinking, I think there needs to be a part 3 where we kind of put all this together, and maybe I show you an example on real data, but I also don't like committing myself to a specific video. Oh well. Next time I'll summarize everything that we've talked about and then teach you a systematic strategy you can use to build models from visuals. And as a reminder, if you are interested in taking a class with me, where you can ask me live specific questions about things that you get stuck on, you can ask me about any of your own data sets. And if you want step-by-step guidance on building the expertise to analyze data, then please visit simplistics.net, where I'm teaching both live classes where you get to interact with me, as well as self-guided classes where you get to learn at your own pace. So yeah, with that, I guess that's all I got to say today. Peace out.